Okay, let's get started. So, what did we learn last time? We learned Cochise inequalities for the derivatives, right? So, given f from omega into r holomorphic, and we have a ball of radius r, z0, whose closure is contained within omega, then we have the following, that if we take the kth derivative at z, it is k factorial over 2 pi I integral around the boundary of the ball of radius z0 of f of zeta zeta minus z to the k plus 1 d zeta. Yeah, that's what we proved last time. Yeah, and this is a generalization of the Cauchy integral formula itself. Just when we take k equals 0, right? We take k equals 0, 0 factorial is 1, and then this exactly becomes Cauchy integral formula. Yeah, cool. All right, so there are many cool consequences of this and of Cauchy integral formula. First one is the one we already talked about. Implicit in this is that we have all higher order derivatives. So we now are dealing with functions that are infinitely differentiable. So we don't have to worry about any order of derivative existing. They all exist. That's part of this theorem. Another thing is the following estimates. So theorem. If we have the same setup as before, well, actually just write it again. So suppose f from omega c is holomorphic, and again we have a ball like this whose closure is contained within omega. Then if we take the absolute value of the kth derivative, actually let's make it around z this time. If we take the kth derivative of this thing is going to be less than k factorial, the supremum of f around the boundary of the ball at z and divided by r to the k, like this. So what does this say? If we have some region like this, you know, and we have some fairly big ball we can put inside it, you know, then the derivative, or any order of the derivative, is flattening out. It's getting smaller and smaller and smaller. We're assuming r is bigger than 1. And in fact, the higher order derivative is the flatter it gets. Yeah? And this is kind of the opposite of what we expect for an arbitrary function. When we have an arbitrary function and we differentiate it, normally the derivative gets worse, right? It gets wilder and wilder. Square root, differentiate, you have x to the half, x to the minus a half, right? Typically, derivatives are worse than the actual function. Yeah? But in this case, the higher derivative we get, the flatter, the smoother it is getting. Yeah? And this also seems somewhat strange, somewhat counterintuitive. And I'm going to spend a bit of time motivating this. So firstly, we'll prove it. The proof is very, very simple. It follows from this. And then we'll explain why you can anticipate some result like this. All right, so proof. Just from Cauchy integral formula, so this is for derivatives if we just take the absolute value sign and put it through the integral, so we're going to have k factorial over 2 pi, and then we take the absolute value sign inside this. Well, we know that this is a contour integral, so this thing is less than the length of the curve times the supremum of this thing inside over the curve. That's one of the basic estimates we proved, right? So then this is less than the length of the curve, so 2 pi r, and then the supremum of the absolute value of f of zeta over zeta minus z, the k plus 1 absolute value for zeta on the boundary of the ball, which is our curve, right? This is one of our basic estimates from when we introduced integration on curves. And then what is this? Well, zeta is on the boundary of the ball of radius r, right? This is r, this is zeta right here. So the absolute value of zeta minus z is just r, yeah? So then this thing is just equal to k factorial. The 2 pi's will cancel, so let's put this. Let's put it at the end of the board. So this is equal to k factorial times r, and again, the absolute value of this thing here is just r to the k plus 1, so we can just pull it out directly. It doesn't care about zeta anymore. So then this r will cancel and it will be replaced by r to the minus k. And then this thing will just be the supremum. Let's just write this, the supremum around the boundary of the ball of radius z of the absolute value of f, which is exactly our estimate. Yeah? So it follows extremely easily just from the formula. Okay, so that's the proof. Let's try and motivate it. So now that we have higher derivatives, we can do the following. So let me subsection this, connections to PDEs. Maybe connections is not the right word, because what is actually going on is that underlying these theorems are theorems about PDEs. So how are these things connected? If we write f in this way that we've been doing, okay, then we have the Cauchy equations. And what do they say? They say that u of x equals v of y, and u of y equals minus v of x, right? So if we take u of x, the partial derivative, second partial derivative with respect to x of u, that's equal to v of ux, right? And if we do u of yy, then that is going to be minus v of xy, right? Which we're allowed to do because now we have all orders of derivative exist. So that says that u of xx plus u of yy is equal to 0, yeah? And this equation, u of xx plus u of yy, is the Laplacian, which you might have seen, or hopefully you've seen. So the Laplacian of u is exactly this equation for a function u from R2 to R. If we're doing from Rn to R, then it is the second partials of all of the coordinates added together. But in 2 dimensions, this is the Laplacian. Okay? So our equation is Laplacian of u is equal to 0. And functions that satisfy this are called harmonic equations, or harmonic functions, I should say. Yeah? Have you seen this stuff before? Have you seen the Laplacian? A little bit. Okay. Cool. So we have this, and the same thing is true for v, as you might expect. So v of xx from this one is equal to minus u of xy, and then v of yy from this guy is equal to u of xy. So we have that Laplacian of v equals 0. Okay? So if we have a holomorphic function, then the coordinate functions u and v satisfy that Laplacian equals 0. They're harmonic functions. Okay, cool. Now, why is this helpful? Well, this is a ubiquitous partial differential equation that occurs in many areas. It is one of the basic models of a partial differential equation. It's a so-called elliptic partial differential equation, which means it has particularly nice properties. And one of the places it occurs is in the heat equation, or as part of the heat equation. So let's talk about the heat equation. So I don't know how much physics you've learned. You don't have to have learned much, but you're aware that we have we have a law that describes the way that heat moves in space, right? That's been around for a long time. And how do we model this? So let's imagine we're in a two-dimensional world, okay? And let's have u of x, y, t be the heat of a particular point xy at time t in our two-dimensional world. Yeah? Heat equation. So let u, x, y, t be the heat at xy, or the point xy. Yeah? And as you know, heat moves, right? It diffuses. It goes from the hot to the cold. Yeah? So we have an equation to describe this, and it's one of the nicest equations we have in physics that is completely not a simplification. It's absolutely describing the reality, and it's the heat equation. And the heat equation is as follows. So heat equation is that u by dt, the partial with respect to time, is equal to the Laplacian. Okay? That's the heat equation. Imagine we lived in a two-dimensional world, and then this, okay, let me erase the board and get a bigger picture. So imagine we lived in our two-dimensional world. So, yeah. And we have a heater and a window. So here is the heater, and here is the window. Okay, so the heater is creating heat, right? And the window is cold. That's where the heat is gradually going to diffuse out of. But the heater is on, it's continuing producing heat, right? And then that heat is going to diffuse slowly over that direction, yeah? And if we lived in this world, I mean, this could be our classroom. We could be like sitting in here in the real world, if post-pandemic, pre-pandemic, right? And we'd be like sitting around, moving around. And we also have the heat of our bodies. We're moving the air around, right? Yeah? But if we just stopped, if we were just completely still, then nothing else would be affecting the situation except the heat equation. Yeah? So whatever heat there might have been around here because we brought it in or we're moving around, shifting the air around, it will gradually diffuse towards the steady state, because this is an equation that evolves with respect to time. Right? So if you imagine us sitting in here in the classroom and keeping completely still for whatever, 5 hours, yeah? Then the heat around the room will be fairly close to constant, right? It's coming out from the heater and it's diffusing out towards the window. Yeah? And if we waited an infinite length of time, it would actually be completely constant because nothing would be changing. Yeah? So that would mean that this part would be 0 because the heat is not actually changing with respect to time. So it's different at different points in the room, yeah? But it's not changing with respect to time because we've reached a steady state. Yeah? So letting t go to infinity, we reach a steady state. Where the heat is not changing at any point in the room with respect to time. So at different points in the room, it's different temperatures, obviously, but it's not actually changing with respect to time. And then so we just have that the heat, the steady state of the heat distribution satisfies the Laplacian. Yeah? Satisfies the Laplacian. Yeah? So this is like hot and the heat is diffusing outwards like this. So imagine U is like a large value around this thing here. Yeah? And the window is cold. So we have a function which is high and then decreases towards this. Yeah? That's what we expect as we let time go to infinity. Yeah? Yeah? And at that steady state, we would expect the thing to do this as smoothly as possible, right? Nature is parsimonious. It will, as smoothly as possible, diffuse the heat from the hot to the cold, yeah? And there will be as little oscillation, as little perturbations as possible, right? The perturbations will be smoothed away as we just let this heat profile reach its steady state, yeah? Which makes it reasonable, makes it believable for us that the more spaced out these things are, right, the bigger R we can put around here, yeah? The smaller the higher derivatives will be, the first, the second, the third, right? Yeah? Yeah? So that is a reason why we would expect things that satisfy the Laplacian to have, if you believe that this is a good representation of the steady state of the heat equation, this is a reason why you might expect this to be true, that we have this estimate that if we take the kth order derivative, then it is less than k factorial, the supremum around the boundary of the ball of radius r of the function itself, divided by, in this case, r to the k, like this. Yeah? That might seem believable. And what's also true is that functions that satisfy Laplacian have the mean volume property. Also, if U is harmonic, then if we take some point, then this is the same as the average around the boundary of the ball of the function, and I'm going to write h1 of c. So we talked about this when we talked about the meaning of Cauchy integral formula. This is just a one-dimensional integral around the curve divided by the length of the ball, right? So if we had a parameterization, so if z of t, which is equal to, oh, I should maybe write, since I'm carefully doing x and y, let's write x0, y0. If we had x of t is x0, y0 plus r of cosine of t, sine of t, that's a parameterization around this curve, right? So from your knowledge of multivariable calculus, this thing is just the integral like this of 1 over 2 pi times r of u of z of t, absolute value of z prime of t, dt. That's what you've learned from multivariable calculus, and we talked about this briefly at one point as well. Yeah? So that's what this means, and I write h1 because later you'll learn that the correct way to integrate one-dimensional curves or over one-dimensional curves is with something called Hausdorff one measure. So just to get you used to this notation, just because I'm used to writing this properly, I put it this. But this is how you should think about this, just having learned multivariable calculus. Because when you have a smooth curve, however you integrate it with Hausdorff measure or this way with the parameterization, it turns out to be exactly the same. Okay, back to this. So we have this is true for something that solves Laplace's equation, something that's harmonic. And that's a simple calculation, but again, from the idea or from the model of or from thinking about solutions of Laplace's equation being steady state of the heat equation, this seems reasonable because look, if we are here, right, and we have the heat is flowing across like this, then at some points around the boundary here of or some points around the boundary of the ball, we're going to have the hotter, right? And then some points over here, we're going to have the colder, yeah? And it seems kind of reasonable that the thing in the center will be some kind of an average of what we have around the outside, yeah? In fact, however you situate your heaters and your windows, however you draw the ball, you'll always see that in the center of the ball, it'll be some kind of an average of what's happening, yeah, as the heat diffuses across. But what is remarkable and kind of fascinating is that it's absolutely an exact average. So that means if you were in your room and you took a soccer ball and then you stuck a bunch of heat sensors around the outside, and then you just recorded the heat distribution around the soccer ball as you leave your room to approach the steady state of the heat distribution. And then you integrated over these recordings, divided by the surface area of the soccer ball, you would find exactly exactly the heat in the center of the soccer ball, yeah? For any size soccer ball. Yeah? So this is an example of math forcing the universe to be in particular ways, particularly symmetrical ways. If you talk with a physicist, they might say, well, that's a consequence of the heat equation. But as a mathematician, I would say, no, this is a consequence of the fact that if you have the heat equation in a steady state, then it satisfies Laplacian, and it's a mathematical theorem that something satisfies Laplacian, satisfies the mean value property. Yeah? So this thing, the fact that you have a harmonic function satisfies the mean value property, essentially reduces down to the divergence theorem, which is just a generalization of the fundamental theorem of calculus. So these mathematical laws imply something about the real world that you probably wouldn't expect. You wouldn't expect exact symmetry, exactly that averaging over the surface of a ball, of the boundary of the ball, would give you the exact temperature in the center, but that's a true thing because the math forces it to be that way. The math forces that thing to be true. And it's just a little toy example, but is it example that there are examples there are examples everywhere in nature, in the world, where things are of particular structure because there is an underlying mathematical law forcing them to be this way. If you look around and you look at the planets and see perfect spheres, there's a mathematical reason why. So maths is this underlying order forcing the universe to be in particular ways. And we don't really get much, there's not widely understood. People understand that physical laws force the universe to be in particular ways, but underneath these laws are mathematical laws forcing an even more fundamental structure to be there. And if you're aware of it, you see it all the time. And if you're not, then you just don't notice it. Anyway, that's an example. So given this thing, we can sort of believe this mean value property. And as we learned, Cauchy integral formula, in the case where we take the value at the center of the ball, just reduces down to the mean value property. Right? Yeah. So we've proved Cauchy integral formula, but from this kind of model or this reduction to this physical situation, we can kind of believe it, at least from the case when the value is taken to be at the center of the ball. Yeah? One of the homework exercises I'll give you in your next homework, not this one coming up on Saturday, but the following one, is to do the reverse. So to go from the mean value property for solutions of Laplace's equation, harmonic functions, and prove Cauchy integral formula. And it's straightforward to do that in the case where you just stick the value directly in the center of the circle, because you just reverse the implications I did. Everything was just an equality. It's trivial. But to do it in general is also possible, and a hint is to use the keyhole contour. So it's actually the fact that these things are equivalent if you have enough integrability to actually deduce the Laplacian. So we need Cauchy integral formula to prove the existence of higher derivatives of holomorphic functions. But if you have a holomorphic function, which just by some reason you're given that it has a second derivative, then you can deduce Cauchy integral formula from the mean value property. And that's going to be something you're going to see. And this is an example of what I've been saying, that a lot of these complex analysis theorems that actually predate PDE theorems are just representations of a larger phenomena that is occurring from a different field, from something called PDEs. So that's one example. All right. Another brief thing about Laplacian that will make this estimate seem more reasonable. And that's the following. So look at this. So suppose we have a function. We have u from some domain, nice connected domain with the boundary omega into R, and u xy is equal to f of xy on the boundary. Okay, where f is some given particular thing, particular function. Okay, in fact, let's consider the class of such functions. So consider let's call it f of little f omega, the family of all such functions. Family. I don't know how to spell family. Something like this, right? Family of all such functions. Okay, good, thank you. And then let capital F of u be the integral of the gradient of u squared dx. And we want to minimize capital F, I shouldn't use F twice, let's call that G. Or let's call it E. We want to minimize E over this function class, okay? And we want to E over capital F of omega. Okay. Let's assume we can do this. Suppose we find the minimizer. Suppose U is the minimizer. And then let phi be this twice differentiable function with compact support contained within omega. So I write it like this. So that means that this guy is only non-zero on some set which is strictly inside omega. Okay? So in particular, f of xy equals 0 on the boundary of omega. Okay? And then let, say, w of t be the integral of omega of this thing plus t times this squared. I'm gonna write dx dy, I guess. Dx dy, just because I'm using this. Okay, Now, u is meant to be the minimizer, right? So u of t0, say that again, u of 0 should be the smallest value as we move around t. Yeah? Because as we move around t, we still satisfy the same boundary conditions. Because this thing is 0 on the boundary. Yeah? Do you see what I mean, people? Give me a thumbs up if that makes sense. Yeah? So now this is just a function of one variable. So expect that w prime to be equal to 0, because when t equals 0, that should be the minimizer. That should be at least a local minimizer of this thing, right? So expect this to be true. Yeah? But if we differentiate this thing, let's see what happens. Well, we can expand out w of t, and then we get this. Just expanding out this expression here, yeah? So we can differentiate this thing easily, yeah? Because this is constant, this thing is just this thing, and this thing is this thing. We just pull out, we just have a quadratic equation, right? We just have a quadratic equation. So w prime of t, when you differentiate it, this is a constant term, it's not relevant. This is the only thing that remains. This thing is just going to be 0, right? So this is the same as having this, that is equal to 0. So here's a little formula you can just check for yourself. If we take the divergence of u, if we take the divergence of gradient of u times phi, then that ends up being the Laplacian times phi plus gradient of u dot this thing. It's just a little calculation. You just take the partials on each one. Okay, maybe I just do it. So because what is this? Because divergence of the first coordinate functions ux phi, uy phi, and then we have uxx phi plus ux phi of x plus uyy phi plus uy phi of y, right? That is this calculation over here. Yeah? So then if we apply the divergence theorem, because this thing has got 0 boundary values, we have that the divergence of this thing, so the integral of the divergence of this guy is the integral around this of gradient u phi, the outward pointing unit normal, which is equal to 0, right? Just the divergence theorem. And this is also equal to the following thing. It's equal to the Laplacian of u of phi plus this expression, dx. And that's the expression we had over here, which is equal to 0. So this is the equation we get from the fact that the derivative of w at 0 is just equal to 0. And then up here, I've written the gradient of u times phi, and I take the divergence of this. So gradient of u is a vector field, right? It's consisting of u of x, u of y. So then if we multiply by phi, then we have this vector field u of x times phi, comma, u of y times phi. Yeah? And we take the divergence. Yeah, we're going to have two terms as we act on each one of these products. U double x phi plus u of x phi of x. Yeah? And then u double y phi plus u of y phi of y. Okay? And then that's exactly this formula, that the divergence of gradient of u times phi is equal to the Laplacian, because this thing here is the Laplacian. times phi. Yeah? And then gradient of u dot product gradient of phi, because this thing here is gradient of u times gradient of phi. Cool. All right. These are just calculations. If you can't follow as I talk and you take notes at the same time, which I wouldn't be able to, then just watch over this video. These are just very elementary calculations. You'll agree with this. Okay, but the point is that this equation now reduces to, and then by this equality, okay, we have that this thing is equal to 0. So this thing, which is this thing, is minus this guy, which is equal to 0. So this thing and this thing imply that integral of this times phi dx is equal to 0 for all phi, which are compactly supported and smooth inside of omega. Okay? Cool. Now, so we're making lots of assumptions here. If the Laplacian is just a continuous function, and whenever we integrate against another function, we get 0, the only way that's possible is if Laplacian itself is equal to 0. So if is continuous, this implies that Laplacian of u equals 0. Because imagine if that's not true. We just take some point where the Laplacian is, say, positive, could be negative, whatever, and just take a little phi, which is supported around a tiny, tiny little ball, yeah? Where this function is positive, but almost constant because it's continuous. Yeah? And then if we just test this guy, if we just take this little compactly supported function phi around this point. So this is a point where Laplacian of u of x0, y0 is, say, bigger than 0. Say it's over here. We put a little function which is just supported in a tiny neighborhood around it. Yeah? And our function is positive. Yeah? Then there's no way that this entire thing can be 0. Yeah? Unless that's actually not true, unless the whole thing is 0. Yeah? So if the Laplacian is actually continuous, then this being true for all test functions, for all functions phi, means that the Laplacian has to be 0. Okay? So what we've learned is that if u is a minimizer of this energy, then u has to satisfy Laplace's equation. That's what we've learned. Yeah? Okay, now let's go back and think about calculus. So when we do calculus, so I should have perhaps raised the board. When we do calculus, we learn a lot about minimizing stuff, right? So if we have g from, say, Rn to R, right? And suppose g has a local minimizer at some point, say, now I'm just going to say x for this vector. So suppose g has a local min at x, then we know that g prime of x is equal to 0, right? Very happy with that, I hope, right? That's just multivariable calculus, yeah? What we're doing here is an infinite dimensional version of this very simple thing, yeah? Because now our space Rn is replaced by an infinite dimensional space, the space of functions like this. So later, or perhaps now, you're learning about function spaces. This is an infinite dimensional space. Yeah? And our g is this energy acting on this infinite dimensional space. Yeah? And if we assume it's a minimizer, even just a local minimizer, what this little calculation was just the equivalent of doing this, and this equation here, this equation here has its analog with this. This is the analog of this. Okay? Okay? Cool. But if we take some explicit g, then, and we have this, then what is this? This is a vector equation, right? So it actually says that this vector is equal to 0. So implicit in this is n individual equations, assuming all the partials of this exist, right? Yeah. This thing is an infinite dimensional equation. Now, I slightly wish I hadn't gone into that direction because it means explaining more stuff and I'm taking you further aside. This is the exact analog of this, except this is a finite dimensional equation and this is an infinite dimensional equation. Okay? All right. So this is a little glimpse into the future if you study analysis, which I hope you all do. Why did I talk about this? Well, because it's another way that we get Laplace's equation out. Yeah? And it's another reason we expect Laplace's equation to smooth things out, because we're minimizing this energy, right? So let's go back to where we started. We have some domain like this. We're minimizing this energy where we fix some boundary values. Yeah? So maybe it's higher here and lower here, and we're trying to minimize the gradient squared. Yeah? Yeah? And it should seem reasonable to you that if we do find the minimizer, something that does it, then it's going to be the thing that's going to be as smooth as possible, right? It's going to flatten out as quickly and as smoothly as possible while still satisfying the boundary data, right? So imagine you have some kind of like ball, draw a ball on your table in front of you, and imagine the boundary values are higher at some point and lower at some other point, yeah? And then you're trying to minimize some kind of a surface which has those boundary values, but connects them through the center, through the area of the ball. Yeah? Then it's going to smooth out things as quickly and as efficiently as possible. Yeah? Yeah? So Laplacian is, by its very nature, something that smooths things out, that makes them as flat and smooth as you can possibly have, right? So by definition, we are minimizing. We're trying to do the very best we can. And the very best we can would be something really, really smooth, right? Yeah? Yeah? If there's any kind of additional perturbations, then that's not doing the minimizer's job. We can make it flatter. Yeah? Okay. All this stuff is not, strictly speaking, complex analysis. This is all background or connections. So this won't be in the prelims. I might ask you some simple question about background in the midterms, because I want you to pay attention to this. Just generally, as professional mathematicians going forward, I also want you to develop a certain breadth. So there's a lot of good stuff that comes from being interested in more than one area. So when you start your PhD and you get specialized in one thing, and this is a mistake I made when I was doing my PhD, you get very into it and you don't learn about anything else. That's a mistake, because taking interest in other areas will really help your research. It might not feel this, but it just really will. So this is important. This is what I do want you to understand this. I don't want you to do just like, oh, this is not really part of the course. And this isn't actually hard. This is, if you go through this, if you feel comfortable with your multivariable calculus, this will all make sense to you. It's just elementary things. And this gives a kind of hint how closely connected this subject is to other things. And that's true for many other subjects that there are this spider web of connections throughout math, between areas that you don't even expect will be particularly connected. And this is just some examples of this. We were talking about the heat equation. Now we're minimizing this thing. It seems a completely different game, right? But it ends up giving us the same equation. Yeah? And it's also the equation we get for the u and the v of a holomorphic function. Yeah? Cool. Final thing before I raise the board. In this is a formal explanation. I skipped over a lot of things that are needed to make this rigorous. It's not obvious that there exists a minimizer, okay, because the function class of things that are one-time differentiable isn't compact. sorry, it isn't complete, also not compact. No, yeah, also not compact. So it's not clear that there is a minimizer. There needs to be a wider notion of function space to allow this to be true. If we do have the minimizer, it's not clear that it's going to actually be regular enough to do any of this stuff. There are theorems that allow you to prove this. But all of these technical things that I skipped over can be gotten around. You can actually do all these things. And this thing is part of a subject called calculus of variations, because this is a variation, right? So when we take this little perturbation here, we're varying something, and we're doing some calculus to extract out some equation, extract out some consequences for the minimizer. Yeah? So that is one of the areas I actually work in. So, and it's a big area. It's very connected to many things, both in physics and in maths. All right, so that's enough background. Now we are going to erase the board, and we're going to prove some consequences of Cauchy integral formula. We're going to go back to mainstream complex analysis as soon as this board is cleaned. Now, let's do the following theorem. Suppose f, is holomorphic in omega, and we have a ball. Let's put around z0, z or z0. Let's just do z. Contained within, I said omega. Then we actually have that f has a power series expansion. That f of z actually z0. Yeah, z0. F of z is equal to the sum from k equals 0 to infinity of ak z minus z0. Let's write that better. To the k, where these coefficients are the coefficients you would expect that you learn from just learning about Taylor expansions for functions just from R to R. Okay, and this is true for I shouldn't say brackets, for any z inside the ball around z0, like this. Proof. Okay, so as I said before, we have now that there are infinitely many derivatives just as a consequence of the previous theorem. This is much stronger. Now we actually have that these things are analytic. We can expand them in a power series. So this is our domain, and we can fit some ball inside here. Then for anything inside this ball, then we can actually expand it out into this power series. Yeah? And the coefficients depend on the center of the ball, right? So if you want to consider something over here, then you still have that it's analytic, but then you have a different power series expansion. Yeah? They might turn out to be the same, but you don't necessarily know that just from this formula. Okay, so why is this true? Well, we have from Cauchy integral formula the following. Integral 2 pi I around the boundary of the ball z0 of f of zeta minus z d zeta. This is Cauchy integral formula, let's write it like this. And we're going to have zeta minus z0, z0 minus z d zeta, like this. So we're just adding and subtracting z0 at the bottom. Obviously that doesn't change anything. And let's write it like this. Let's factor out this. Let's factor out this z minus z0. Okay. So then we have, zeta minus z0. Let's factor out this guy. So then we're going to have 1 and then plus z0 minus z over zeta minus z0. Yeah, just doing some algebra here. And now let's write this as minus minus so that we can write z minus z0. So if we do that, then this becomes like this. Like this. Yeah? Cool. Now, what do we know? So let me do a bigger picture. This is our ball. This is z0. We're integrating zeta around the outside, right? This is zeta. Yeah? And z is something here. Z is something here, right? So this complex number, zeta minus z0, has absolute value given by the radius of the ball. Yeah? And the radius of the ball is r. Yeah? Where the absolute value of z minus z0 is strictly smaller than that. Yeah? So this complex number here, z minus z0 over zeta minus z0, is a complex number whose absolute value is less than 1. Are you all with me? Yeah? Give me a thumbs up if that makes sense to you. Yeah? So notice that for any zeta around the boundary of the ball, then absolute value of z minus z0 is strictly smaller than absolute value of zeta minus z0. So therefore, the absolute value of this number, z minus z0 over zeta minus z0, is strictly less than 1. Yeah? Now, recall this following formula for the geometric series, which follows in exactly the same. I mean, we already talked about it, we actually proved it, that if we take any complex number, let's call it w, we take the sum from k equals 0 to infinity, w to the k, where w is complex, that is 1 over 1 minus w for any w strictly less than 1. Yeah? This is a standard, this is, you learned this in series calculus 2, exactly the same proof holds for complex numbers, and I think we even did it. Yeah? Cool. So, we can apply that to this thing here, because this is 1 over 1 minus a complex number strictly less than 1. Yeah? So, let me put it over here. So 1 over 1 minus z minus z0 over zeta minus z0, yeah, is, by this formula, the sum from k equals 0 to infinity of z minus z0 over zeta minus z0 to the power k. Yeah? Just applying the formula above. Yeah? Okay, so then we can put it directly into this thing. Let's call this thing star. So, star becomes that f of z is equal to 1 over 2 pi I integral around the boundary of the ball of radius r around z0, and then f of zeta minus z0, and then this power series here. Because this power series makes sense, it's convergent, this is a meaningful function in every way. We've already learned it's holomorphic. We have all good stuff about this. We have nothing to be scared of when we write this. This is absolutely a true thing for any zeta around the boundary of the ball. This guy is all good. Okay, and we're integrating with respect to d zeta. Yeah? So, let's take a look at this. So this z minus z0, right, it's not involving zeta. Yeah? So what we'd like to do is to pull it out from the integral and then pull the sum out from the integral. In other words, swap the integral and the sum. And then what we'd have would be a power series in z minus z0. Yeah? That would give us a power series in z minus z0, which is the direction we want to head to. Yeah? But that's not a trivial thing because, again, this power series, it's defined as the limit of the partial sums, right? So what that would involve doing is swapping an integral and a limit. Yeah? And we've learned we can do that when we have uniform convergence. Yeah? Which means uniform convergence of this expression for every zeta around the boundary of the ball. Yeah? And what I will show, and what maybe some of you already anticipate, is that we do have this uniform convergence because this thing is a nice geometric series where this complex number is strictly below whatever. Strictly below the difference between this length and this length, or the ratio of this length to this length. Yeah? Actually, the difference between this length and this length. So you might anticipate that indeed we will be allowed to do that. But I'm going to explain that carefully. For the moment, though, I'm gonna anticipate that we're allowed to do this, and I'm going to show you the formula that we get is the formula that we want. Okay, so if we can swap the sum and the integral, i.e. pass the limit through the integral, then what would happen? Then we would have that f of z would be the sum from k equals 0 to infinity of z minus z0 to the k. And then we'd have the integral, let's put the 1 over 2 pi I over here, 1 over 2 pi I. The integral around the boundary of the ball, like this, of all of this stuff. It would be f of zeta, and then we have zeta minus z0, and then zeta minus z0 to the k, so it's zeta minus z0 to the k plus 1, like this. Yeah? The zeta. Yeah? Cool. Now, this is now our coefficients, right? If we're allowed to do this step, we now have a power series with these coefficients. But they're not the coefficients I claimed, or are they? Are these the coefficients I claimed? I claimed the coefficients were this. And now I have this. So has something gone wrong, or are these actually the same? Exactly, yeah. So by application of Cauchy integral formula for derivatives, this thing, yeah, I put this in blue, with the kth derivative, like this, is just k factorial times this expression. Yeah? 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 So this thing over k factorial is exactly this thing. Yeah? So that means we have exactly the theorem that we want. So this is the sum from k equals 0 to infinity of z minus z0 to the k, a k exactly the result that we want. Yeah? Cool. Are you all with me here? Before I raise the board, everybody happy? Yeah, give me a thumbs up if you are. If you're not, then, and you don't want to talk about it now, then I have office hour Monday from 11:10 to 12:10 and Wednesday 11:10 to 12:10 in my personal WebEx room, this room. Just show up there. Just turn up, ask me the questions. If this stuff is not making sense, it's only going to make less sense going forward, so just nail it down. Watch the video over, write down what is unclear to you, make a note specifically what's unclear to you, then come to my office hour and ask me about it, okay? Don't let this thing just drift in some kind of not clear place for you, hoping that later it's all going to fit into place. The exact opposite will happen. If you have areas of misunderstanding, they will expand as we go forward. So close them down as quickly as possible. Watch the video, make notes, come to my office hour. You will understand this, I promise you. Cool. So we want to pass through this limit. Yeah, we want to pass through this limit. We want it to be uniform with respect to, well, let me say that better. So this thing is the following partial sum, right? This is the limit as n goes to infinity of this partial sum, right? That's the meaning of this infinite sum, right? So this partial sum here is a limit, and it depends on zeta, right? Depends on zeta, yeah? So we can write this thing, so we're going to write that, we're going to write Sn of zeta. So z we're just taking as fixed. We take it inside the ball. It's not moving. We're just going to establish this for our particular choice of z. So we write this thing is this partial sum, the sum from k equals 0 up to n of z minus z0 to the k over zeta minus the k plus 1 times f of zeta, like this. Yeah? We're going to write this as this partial sum, and what we want is to take this limit out. So this is 2 pi I, and then this is the integral around the boundary of the ball, like this, of the limit as zeta, the limit as n goes to infinity of Sn of zeta d zeta. Yeah? Now, if we just had Sn here, right, then it's just a finite sum, and then we can swap the summation and the integral. That would be fine. Yeah? So the real issue is passing the limit out. Yeah? Yeah? But we've learned that if for all zeta living around the boundary of this ball, so this is our ball, right? Radius r, and zeta lives right here. We've learned that as we consider all these zeta around the boundary of the ball, if this expression uniformly converges to its limit, which is this infinite sum, yeah, then we can do it. Then we can actually do it. That's what we learned, that's what we did last time. So when we have a sequence of functions, yeah, let me put it over here. So if Fn tends to f uniformly on gamma, yeah, then the integral Fn dz, the limit of this as n goes to infinity over gamma is just this thing. This is this little calculation, and it just follows from taking the absolute value signs inside, right? So uniform convergence allows us to pass the limit through the integral. Yeah? Is this coming back? Yeah? That's how we proved the Cauchy integral formula for the derivatives, right? That was the last step we had to do. Yeah? So all we need for this to work is that this thing, the partial sum, this expression over here, has to tend uniformly, independent of the choice of zeta, to the limiting function, which is the infinite sum right here. Are you with me, everybody? Everybody happy? Cool. All right, so let's take a look. So let me write that in words. So to pass the limit through the integral, we just need so I'm going to write S infinity for the actual infinite sum, that S n tends to S infinity uniformly on the boundary of the ball, like this. Cool. Now, let's see what S infinity minus Sn looks like. So we're going to define the remainder term, Rn, like this. We're going to define it to be S infinity, the entire sum. So actually, let's make sure we are clear that all this stuff depends on zeta, because it has to be independent of zeta. It has to be uniform in zeta. So Rn of zeta, we're going to define it to be the infinite sum minus the partial sum. Yeah? And then from this expression, what's that? That is the sum from k is equal to n plus 1 to infinity of all of this stuff. Let's write it like this. Z minus z0 over zeta minus z to the k, and let's write this, f of zeta over zeta minus z. 1 second. We had, it's not zeta minus z, it's, yeah. There we go. Thank you. Zeta minus z naught, like this. Cool. So this is our expression like this. Yeah? This means that the remainder is exactly this. Yeah? Cool. So let's be very, very careful, because this itself is defined as an infinite sum. So let's define this. N, and let's put an M. So take the finite sum like this. Yeah? Where M is bigger than n. Then we can estimate this thing, right? So the absolute value of our m n of zeta is just, we're going to put the absolute values through this thing. It's a finite sum. We don't have to worry about taking absolute values through it because there's no limit involved. It's now a finite sum. So then this is less than, I mean, it's going to be fine because absolute value is convergent and the sum's convergent, but that's what we're about to show. So I don't want to muddy the water here. And then the absolute value of this thing, z minus z0 over zeta minus z0, like this, to the k, and then the absolute value of this thing, and then this thing, absolute value. Okay? This thing is, so z is fixed, zeta is going round the circle, right? So here is z, maybe, yeah? Yeah? I mean, z can be anywhere. It can be really, really close to the boundary here. Yeah? But this number, yeah, is always less than some particular number less than 1. We have that z minus z0 is less than r minus something. So let's write that down. Z minus z0 is less than, say, 1 minus delta times r for some delta. It's just true. Yeah? And then zeta minus z0 is just equal to r. So this thing here is less than just 1 minus delta to the k. Yeah? So then this thing is less than the sum from k equals n plus 1 to infinity, just 1 minus delta to the k. Yeah? This thing here, it's just equal to r itself. Let's put it here. We're summing with respect to k. And this thing is less than the supremum of the function f on the boundary of the ball. So the supremum of the function on the boundary of the ball of radius z0, like this. Yeah? Everybody with me? Yeah? So you can just pull out this thing and this thing. So then we have the supremum of the boundary of the ball z0. We have f, and then it's divided by r, right? And then we have this thing. We have the sum from k is equal to n plus 1 to infinity of 1 minus delta to the k, yeah? And what's this thing? This is just the supremum over the boundary of the ball of z0 of this over r, like this, and then this thing is 1 minus delta to the n plus 1 over 1 minus delta, so like this. Yeah? So this thing here, by our geometric series stuff that we know from Calc 2, is just equal to this. Yeah? Cool. So for sure, this thing is going to 0 as n goes to infinity, because 1 minus delta is going down to 0 as we take higher and higher powers. Yeah? And it doesn't notice anything about zeta, right? This is independent of whatever zeta is. Yeah? Yeah? Cool. All right, good. So that means that we can actually consider a Cauchy sequence like this. So for any fixed zeta, so Sn of this forms a Cauchy sequence, because this is exactly estimating the difference between Sm and Sn. Yeah? And we know it's going down to 0 as m and n goes to infinity. So this is a Cauchy sequence, and it's going to converge to its actual limit, which is going to be S infinity. So this thing converges to S of infinity of zeta. Yeah? And infinity n of zeta equals the limit. So that's your value signs like this, equals the limit as m goes to infinity of m n of zeta, just by definition. Yeah? And the absolute value is continuous, right? And we have that this thing is indeed converging to this thing because of this estimate. So this is equal to the limit as m goes to infinity of this guy. And this guy is always less than this particular estimate, some constant times 1 minus delta to the n plus 1. So I'm running out of space, so I'm putting everything here which and putting everything which isn't the 1 minus delta dn plus 1 just as a constant, because it's not moving with respect to n. Okay. So that's what we want, because we have that this thing, which is the remainder, which is the difference between the partial sum and the actual infinite sum, is uniformly bounded. This doesn't depend on zeta. This doesn't depend on zeta. Yeah? This is independent of zeta. So we can just guarantee that for any zeta, this thing is as small as we like by taking n to be large enough. Yeah? So we do indeed have that the partial sums uniformly converge to the actual sum. Yeah? And this allows us to do this exchange, to take this limit outside this integral, and the last equation we wrote on the previous board gives exactly the expansion. So we've proved the Taylor expansion for holomorphic functions, and it followed really easily from just Cauchy integral formula. Okay, so just as before, the actual formula is really easy to deduce. We just have to do a little bit of work to make sure that we can swap the limits of the integral sign. Just exactly the same issue was with respect to deducing the Cauchy integral formula for derivatives. The formula itself was just natural, just consequence of the algebra, but making sure that we could pass through the limit was a little bit of extra thought. So we have this. We have that holomorphic functions are actually analytic. They have a power series expansion around every single point in their domain, right? And once you have a power series, then it has a radius of convergence. It might be bigger than the actual domain. Yeah? So sometimes we'll have a function which is defined on some domain. We'll have a power series expansion, and we can actually define it outside of its domain. And that's another topic that we will discuss going forward. All right. So sorry I overrun. Hopefully this stuff is clear to you. Again, go to my office hour if it's not. Otherwise, I will see you all on Thursday. All right. Bye-bye, people.